Okay, good morning to everybody. I propose to start training course for young researchers. I'm L.Grundwaldt from Geoforschungszentrum or Geo Research Center, Helmholtz Center. This is a large-scale research facility in Germany from Potsdam, not far away from Berlin. It's my task to give you some ideas about basic principles of laser retroreflector design. We have plenty of time. I will not speak 1.5 hours uninterruptedly. I have been a student myself, so I know how boring that is and how stressing, especially on Monday mornings. So I think we will make some intermediate breaks as well. And a second proposal, I will try to make it as slow and as good, understandable as possible, but in case there is any immediate question, please raise it so we can discuss. I have about 25 to 30 slides. This is not the majority, so I will not stress you too much with that, but I would like to give you an idea that it's not so simple to design a retroreflector, which on the first view looks very simple. I have here an original sample. I will give it around. This is a 28mm clear aperture cube corner or a triple prism, as we call it. It is a hexagonal form, which is quite unusual for space applications, but it is an original one designed to bring light back from a distance of about 800 to 1,000 kilometers to Earth. It was manufactured at the Institute for Precision Engineering in Moscow. They have plenty of them. They make hundreds and thousands of them and have them on stock all time. And in case there is a mission under construction or development, you simply open their shelves and they have it ready. So in case you look there inside, it's nothing very mysterious. You see a single eye. This is always yours. You cannot look around the corner. You will never see the eye of the neighbor. This is the basic principle of a retroreflector, which brings the light back into itself. But what you cannot see with your own eye is the very delicate design in optics, which is behind this simple construction on the first view. This delicate construction, this delicate optical manufacturing modifies the light, which is getting back over, I would not say cosmic distances, but rather large. So, I give you first an overview of the topics I would like to tackle. Short words about the principle of satellite laser ranging. The principle appears as any principle in the world, very simple. The problem comes later, in case you have to deal with the more, let's say, dedicated things which play a role in this seemingly equal or easy method. This is the range equation. We want to know why this is complicated at all, why it's not so simple bringing a laser pulse into space, letting it reflect on some mirror and get it back, why there is such a weak signal to be expected, what we can do to deal with an unavoidable effect, which is called the velocity aberration correction. Then we will look into the optical properties of laser retroreflectors themselves. This is a matter which is rarely taught in physics. When I was a student in Jena University, I also was in an optical course, but I never got a deep insight into the optical properties of laser retroreflectors, because for ground applications, which is the usual thing, they are rather simple and straightforward. The problems come as soon as we want to apply them in outer space. So I will tackle the question, should we use coated prisms? Should we coat the reflecting surfaces with aluminum or silver or any other stuff? Or should we let them unmodified, uncoated? Because the prism will reflect the light, which is incident from the front face, even in case you do not cover them. But in this case, you will see that you get very, very nice effects caused by the polarization of the incoming light. We will see which methods there are to modify the optical properties so that we can use them for application in space. We will see which implication those 2 points, coated, uncoated, modified, unmodified, prisms have for their use in spaceborne laser retroreflector arrays. And we will, and this is interesting for students, have a look if it is possible to verify experimental the far field diffraction patterns we generate with those methods. I will give an overview of design and shape of laser retroreflectors for various mission types. There are satellites at different altitudes. There is plenty of spacecraft in altitudes between, let's say, 450 to 800 or 1,000 kilometers. Then there is a big gap up to about 6,000 kilometers, and then there is another gap, and the space becomes populated with laser retroreflector carrying spacecraft again at altitudes starting from about 19 to 20,000 kilometers. Unfortunately, even if the laser retroreflector appears to be such a simple device, there are corrections to be applied to the laser ranges. It depends on the design, on the, let's say, on the layout, on the optical layout of laser retroreflectors. It is rather simple, or let's say relatively simple, for spherical satellites. A simple ball, a cannonball flying in space and reflecting the light back, doing nothing else than flying, not transmitting any radio signal, not making images of the Earth. It is a little bit more demanding for the range correction for non-spherical satellites, and what is not written here, but which is unavoidable, this is the center of mass correction. And finally, we will sum up with conclusions. So once again, this is a repetition of things we have heard already. The principle of satellite laser ranging is the transmission of short pulses towards the reflector on board the satellite, catching part of the photons back. And the good thing of laser ranging is that you have rather simple observables. If you compare that to the long equations, 2-3 lines of equations you get for GNSS, let's say GLONASS or GPS or Galileo, you find it extremely simple. You have to measure the time it takes the light to travel from ground to space and backward, to multiply it by the speed of light. And because we want to have the range, not the two-way range, we have to divide it by 2. This would be the end of the story in case there would be a perfect station on ground, and in case there would be vacuum. Because we are not living in a vacuum, we have to correct for the part of the laser path it takes within the atmosphere, and we have to take care of the ground station. We have to put a calibration which is dependent on the system on ground which transmits and receives the laser paths. I have not written here the very delicate and small-scale corrections the laser retroreflector itself introduces. This is one of the last topics we have. So in our times, I should maybe modify it from time to time. The laser pulse width is in the order of a few tens of 100 picoseconds. The shortest pulse is used for laser ranging for the moment are 10 picoseconds, and they will not become very much shorter, at least within the next 2-3 years. But maybe, as you have heard a few days ago, there are ideas also here on a project governed by the University of Riga to use femtoseconds for laser ranging to satellites. It would open a fully new field of research, but it is not so simple. For the moment, we are limited to ranges of about 10, 20, 30 kilometers. The double distance divided by 2. We need the surface parameters to perform the correction of the atmosphere, and we need something about the station. This is something I will tell about you in the afternoon. So you get simple observers, as I told you, two-way ranges with an absolute accuracy of less than 1 centimeter. I will not get back to this point, so I stress it here. Why do we have absolute accuracies in comparison to what we get by the apparently simple method of using GNSS, let's say GPS receiver.
Sorry, may I ask?
Yeah.
Why you are applying atmospheric correction with a minus sign, not as a multiplier? Just the deepest reason is that the sea have been changed.
Yeah, but the sea changes only within a certain, a very short part of the laser range. This is only the first, let's say, 10-12 kilometers compared.
Okay.
This is very, very long distance. So
Yeah.
it's much simpler
Okay.
to subtract this short part.
Yeah.
Otherwise, it would be rather complicated because you would have to make the integral over the index of refraction of the atmosphere, and makes no sense to have an integral over a thousandth of the part and then to have it equal to 1. This is the basic idea behind that. Yeah, why it is absolute? The absoluteness comes from the fact that we use only a single clock. In GPS, this is something sometimes forgotten, you do nothing else than comparing clocks. You transmit, let's say, a pattern of navigational signals at a given time and replicate them on ground and shift the clock of your receiver on ground as long as you have coincidence of those patterns and compare, at that moment of this space transmitting time, the signal was sent, and at that moment of ground receiving time it was received. But the signal was sent and synchronized to a different clock than is running on your receiver on ground. That means you have to deal with two clocks which are running not equal to each other. There are not two clocks in the world which are running fully synchronous. In laser ranging, you have a single clock on ground which synchronizes the transmitting moment of your signal and the receiving signal of the moment. And in case you are capable of synchronizing this clock on ground to the universal coordinated time, to better than, let's say, 100 nanoseconds, which is absolutely not demanding today, then you get ranges which are in the along track, because satellite travels with about 8 kilometers per second, to better than a centimeter or a few millimeters. This cannot be achieved by the GNSS for the moment. There you have excellent relative distances, and in case you place two GNSS receivers close to each other that they see the same spacecraft, then you get excellent relative distances up to millimeter with less demanding methods of computation. But you will not get the absolute position to better than 1 millimeter or something like that. That's why we use the laser ranging for calibration and validation of onboard, for instance, GPS or other microwave experiment, which is used, for instance, for precise optical orbit determination. This is what we call POD. So let's now go to the radar equation. We have a satellite in space. Let's assume we would use the complete surface of the satellite, a satellite, to bring the signal back. We have a laser on ground with a certain energy, this is E laser, and we transmit our beam with an angle of diffraction we call theta of transmit beam. We have already written here the receiver area, but we will need this only in the second step. It is necessary to widen the beam. Why? There are two reasons. At first, it is impossible to keep the laser beam narrow over all the paths it travels. In very bad science fiction films, let's say the very first series of Star Trek, you see needle-sharp laser beams going through half of the outer space, half of the galaxy, without any widening. This is against the basic laws of physics. The smaller an aperture is you transmit a light beam through, the faster the light beam will spread. This is the basic law of diffraction. And we use even this effect because our objects, our targets in space, are far away and they are relatively small. We will see later some examples of laser retroreflectors on spherical satellites, but only as an example. The two popular French satellites, Starlet and Stella, goes 24 centimeters in diameter, about the size of a football, to give you an example. Travel with about 8 kilometers per second around the Earth at a distance for the space station, for the ground station, between 1,000 and 1,500 kilometers. So this is about the same as we would try to find or to range to a football placed in the Red Square in Moscow from Berlin. This is about the same distance, so it is impossible to hit the remote target directly, and so you have the only chance to widen your beam to an amount that it fully covers the target. It's even much wider than that, so that you have some chance to follow the satellite across the sky, because you cannot be sure that the satellite will always be visible and you can make direct targeting to the satellite. So this is the way to space, and we have to go back, and then the same happens. The satellite is not capable of keeping the laser signal sharp. So we get now the angle of diffraction, theta set, bringing the laser signal back towards ground. And here we have a limited aperture of the receiver, a receiver, which of course is much, much smaller than the spot on ground, which is illuminated by the signal scattered back or reflected back from the satellite. We have the distance of the satellite r set, and the radar equation, which is very famous, says that the number of photoelectrons you receive is proportional, this is fully clear, to the energy of the laser. The stronger the laser, the more photons you can expect back. It is proportional to the square, to the aperture of the receiver. It is proportional to the square or the aperture of the reflecting satellite or the reflector on board the satellite. It is inversely proportional to the angle of divergence you can apply on ground. The more narrow you make it, the better. It is inversely proportional to the square of the angle of diffraction from the satellite. The same reason applies. And unfortunately, because we are ranging forward and backward, we have this famous 1 over r to the 4th power of the satellite. This is the big problem, and this gives us the trouble in satellite laser ranging. The farther away the satellite, the weaker the signal gets, and it does not get weaker linearly, but according to the inverse 4th power. This is the big problem we have in laser ranging. This is the first problem, and the second is the velocity aberration. Velocity aberration is nothing which was invented or discovered in the field of satellite laser ranging. This is a well-known effect to all the astronomers. In case the Earth goes around the Sun and you are looking to the stars, you will see them at a slightly shifted position during different seasons of the year, because the velocity of light is not endless. So we have a small angle of velocity aberration. The prism, which is moving at a velocity v, this is about 8 kilometers per second in the near Earth orbit, perpendicular to the propagation of the transmitted pulse, will be reflected in a slightly different direction. Also take into account, in case you would move together with a prism, you would not see the effect. In case you are moving with a prism, the light leaves the prism exactly at the same angle as it came in, but unfortunately the ground station is not in an inertial system together with the satellite. The satellite is moving on a circular orbit, and so we get this deflection, which is about proportional. It is not exactly equal, this is a simplification here, but only to give you an idea. 2 times the velocity of the satellite is the orbital velocity of the satellite, 8 kilometers per second, divided by the speed of light. This is about 8 kilometers per second and 300,000 kilometers per second. You see this angle will be relatively small, it's in the order of few arc seconds, but without corrective actions, the signal will miss your station. And so you have to do something, because you cannot modify the velocity of light, you cannot modify the velocity of the satellite for a given orbit. It has to fly with that velocity, otherwise it will fall back to Earth. And so you have to do something. Let's do some statistics. How big or how large is the velocity aberration? We assume an orbit of typical remote sending satellite, 620 kilometers, with an inclination bigger than 90 degrees, 98.4, let's say between 97.8 and 98.5 is a very popular inclination. This is the so-called solid synchronous orbit. This is an orbit where the satellite cruises over your ground station always at the same local time of the ascending node. That means you can even choose your orbit in a way that the satellite is permanently flying along the border between light and shadow, permanently along the dusk dawn, as we call it. This is very nice for satellites which have a large demand in power, for instance radar transmitting satellite. They all continuously put their solar arrays towards the sun in such an orbit at around 98 degrees, practically never go into the eclipse of the Earth caused by different seasons. We assume a perfectly spherical Earth, a circular satellite orbit to make the computation simple, and look what ground stations at different latitudes would say. The simple formula, 2 times satellite velocity divided by the speed of light, is a simplification, as I already told you. In principle, there are 2 components of the velocity aberration vector, but I didn't want to make it too complicated. You have to solve it in a way that you test every second if your satellite is above your station, and in case the elevation angle exceeds 20 degrees, you compute the aberration angle from the velocity components along the orbit and store them, and subsequently you make a histogram for that. And you see a station at the equator would see a slightly different station than at 55 latitude. Okay, Riga is about at 57, but it would look for Riga about the same. The aberration is in the order of, let's say, 25 to 50 microradian. A microradian is a slightly different expression for an angle in optics. Let's say 1 microradian is about 5 arcseconds. 1 arcsecond is about 5 microradian. So this way. So if you sum that up for latitude between 0 and 60 degrees, you see that there is a sharp peak. You always will have, in any case, you have the velocity aberration as large as 50 microradian, and you will not find velocity aberrations smaller than 28, 25 microradian. And that's a pity, because this gives rise to a waste of signal we get back from space. From those 2 things we have to deal with, the radar equation and the velocity aberration, we have some implications. The first is that we have the inverse proportionality to the force power of satellite distance. That means we have to take into account that we need a space segment on board the satellite which is capable to bring a sufficient number of photons back. You need a reliable optical link, and you have to take into account in the first years of satellite laser ranging, there were measurements performed only at night time. The satellite was maybe illuminated, the stations was in the night. The night sky was dark, so the optical link was not so critical, because in case you could distinguish your optical signal from the dark background, it was fine. But today, the demand is to perform ranges at any given illumination, in bright daylight, without any visibility of the satellite. So you need an optical link which is reliable under both day and night conditions. I told already that we have to take measures to mitigate the effect of the velocity aberration. Without doing something like that, and we will see that in the next slides, we will not get anything back. As I already told, we cannot modify 2 of those parameters, and the only chance we have is to modify the design of the reflecting prisms. And we also have to take into account that the spacefaring nations put strict limitations on what we can take on board. The space segment will only be accepted if it is small in mass and size. The reason why the spacefaring agencies like laser retroreflectors is that they are relatively small, that they are relatively low in mass, practically very low masses and sizes. They do not need power from the onboard power supply system. They do not need thermal regulations, and they do not need any radio contact. They do not need, let's say, a radio link. No connection to the onboard computer supply. But a certain size and number of optical elements cannot be exceeded. So, and now Let's have a closer look on what follows from that. We start with the very basic things, the optical properties of a retroreflector. If we observe, and we will see later how we can do that experimentally, the far field of a single retroreflector is perfectly manufactures angles of 90 degrees equal. Then we have the image of an Airy function. The Airy function is the same what you would see behind the screen, where there's a circular aperture in, which is illuminated by parallel lights. You see a very, very strong central lobe. We have here a negative of that, and we have concentric diffraction ranges, rings of the diffraction pattern, which are at defined locations. This scale is again in microradians from the center. This is the central lobe, which is also getting back from space. And you see, unfortunately, here where our signal starts to get interesting, between 25 and 50, the central peak would be somewhere there, outside, above the ceiling. We have low velocity aberration in our region. Very, very few passes only at low velocity aberration in the order of 25, 28 microradians. The velocity aberration has to be overcome by using the diffraction rings for that reason. In the unspoiled version, you have an incoming light ray. Let's say we have a normal incidence to the front face. It is reflected on all three back surfaces and leaves the prism again at the same direction as it came from. This is the basic principle of the retroreflector. But we have to consider now methods to make use rather of the central lobe, which is possible, I can tell you already now, or to find some method to bring energy from this lobe into the diffraction rings. The diffraction rings are at a location which depends on the aperture of the prism. The larger the prism is, the more narrow, with respect to the central lobe, you will find the first diffraction, and so on. And the smaller you have the cube, let's say for a 10 millimeter cube, you have the first diffraction ring already at a distance of about 25, 30, 40 microradians. This is practically the angle of velocity aberration we have to look for, and later we will also have to see that we have to take polarization effects which we have not considered now into account as soon as we are dealing with uncoated prisms. So let's have a look on a spoiled prism. We have a very important abbreviation here. This is DAO. This is the dihedral angle offset. A dihedral angle is practically nothing else than the 90-degree shape of the backside of the prism surfaces. This is just a matter of expression the opticians like. And we look now on the theoretically computed diffraction far field of such a single retroreflector, 1.5 inch or 38 millimeter of clear aperture, and we normalize the intensity of the Airy peak to 1. You see the Airy peak here at the velocity aberration of 0 is not 1. Why that? Because there is an unavoidable loss. In case we do not cover this prism, we will lose 2 times 4% of Fresnel reflection at the entrance and the exit of the prism. This is the same when you have a single glass window. You will never get a transmission of 100% because there's an unavoidable Fresnel reflection. You could do the same as all optics in modern photo equipment are covered with. You can cover it with some dielectric layer, but these dielectric layers unfortunately are not resistant to most of the cases to the optical properties of outer space. Let's say we have a different dihedral angle of 0, then we have what you saw already, the central Airy peak, and the first lobe here, very, very low intensity, 23, 25, about 30, 40 microradians. If we spoil all those 3 angles by 0.7 arc seconds, you see that the central lobe loses energy and more energy is brought into the diffraction ring, and this process tends to continue as the bigger you make the offset of those backward angles. These are theoretical results, but which can be verified very nicely in the laboratory. With an increasing dihedral angle offset, we decrease the central lobe intensity and bring more energy into the diffraction rate. But you see, the result is not just overwhelming. You will never get more than about 10% of the original energy which was contained in the central lobe in this first diffraction rate. So, this is one thing, and the other thing you have to take into account, seen from the satellite, which is moving there at a given velocity, the station which was transmitting and is receiving the signal will be located somewhere on the screen. It could be here or could be there, depending on the attitude of the satellite. That means what we see here, these 10% of the total signal are spread all along this diffraction rate. And this is the reason, together with the inverse proportionality of the force power of the satellite distance, that the signal getting back from outer space is so deep. We cannot use the central lobe, and we have an arbitrary position of the satellite ground station somewhere on the screen, as seen from the satellite. Of course, we could ask what would happen in case we stabilize the satellite in 3 axes. We know that it will be all time, also this active light in this position, and we make a trick. I will not describe this in more detail. We spoil only one of the dihedral angle. Again, a 1.5 principle. We coat the back surfaces, and as in the example before, and we spoil one of the dihedral angles by minus 3.8 arc seconds. Then we get the unique effect that the far field is split into 2 lobes. This time the scale I asked for is in arc seconds, so 12 would be about 60 microradian. Then practically nothing is left in the center. The full transmitted light is split into 2 lobes, and seen from the satellite, the ground station would be in the central lobe, as seen in the velocity direction of the satellite. The other one is exactly at the opposite side. It is lost. It is never accessible for the ground station. But the ground station should see the center of the lobe containing half of the energy. This makes this method quite popular and quite nice in the case of conserving energy. But unfortunately, I told you, in case the satellite, the pattern rotates together with the satellite. In case you rotate the satellite for 45 degrees, this pattern would be here. In case the station is still there, the station sees nothing. So in case the satellite is maneuvering and is performing some yaw steering, this method is not applicable. Let's get back to a single reflector with 3 equal dihedral angles. Now we have an uncoated prism. We let the glass of the prism uncoated. We put no aluminum, no silver, no nothing on the back surface and rely on the total internal reflection. We have learned in school, very early years already at basic school, that there's a total reflection in case you look at the spoon under a certain angle, you will see it only up to a certain angle if you have the spoon in water, something like that. Now you see again the central lobe, but you do not see the ring at the pattern where the first diffraction is to be expected, but an irregular and non-symmetric pattern of spots. We assume for this example that we have linearly polarized light and we have the polarization plane vertical to the prism. So that means we have a prism here sitting with one of the dihedral edges above and have a vertically oscillating laser beam, and look at the far field diffraction pattern, no diffraction angle offset, dihedral angle offset. The same aperture as before, 1.5 inches, 38 millimeters. Now we see at the first that already with no DAO, the intensity of the non-symmetric spots appears brighter than before for the coated prism. The intensity of the central peak is only a quarter of the area peak for a coated prism at the same aperture. I do not have it here on the scale. And now, in case you perform dihedral angle offsets in steps of 0.25 arc seconds, you get more and more irregular pattern. Central peak disappears practically. You get more and more energy into these irregular spots around. But you see also the intensity is not overwhelming. It is in the order of about 5 to 8% of the total energy rest. So that means with a coated cube, the central peak is decreased. In the case of an uncoated cube, the same happens. But the pattern becomes more and more asymmetric, and the dihedral angle offset increases. So you have to think carefully. On the other hand, you have the good thing, we will test it in the next slide. I will go back. That, because we are just comparing coated and uncoated prisms. The optical losses for uncoated prisms are rather low. We have the Fresnel reflection on the front face only, 4%, nothing else. For the coated prisms, we have to take into account the losses in the reflecting material. This we have neglected in this theoretical assumption. We have assumed a 100% reflectivity in each of the surfaces. And because the light has to reflect on all three of the reflecting surfaces, you get this to the third power. And let's say, for instance, the aluminum has a reflection coefficient at popular wavelengths in the order of 80–85%. You get losses of the reflection via the coating material of about 50%. So the optical losses for coated prisms in total are higher. Polarization effects play no role. They are strong for uncoated prisms. And there is something which I can tell you only, I will not go into detail with mathematics. In case the sun is shining into your prism on part of the orbit, part of the sunlight is absorbed into the optical layers you have used to coat your back reflecting surfaces and to bring more light back. It is absorbed there and produces heat and gives rise to thermal gradients. They are higher for coated prisms, they are low for uncoated prisms. The thermal gradients give rise to a distortion of the far field. That means in case your front faces are at a different temperature than your back faces, then you will get a strong modification of your diffraction far field, which is unpredictable. The good thing for the uncoated for the coated prism is the relatively high cutoff angle. In case you, maybe in the coffee break, you take again this prism into your hand and incline it. Up to now we have only assumed a perpendicular incidence of light. You will see that you can incline it to about 50% before you lose the contact to your own eye. This is what we call the cutoff angle. It is relatively moderate for a coated prism. It is relatively small for an uncoated prism because this uncoated prism relies on total internal refraction. And in case you exceed 17 degrees under a certain orientation, you suffer the so-called optical breakthrough. You do not get reflection on all three surfaces anymore, and the optical contact is lost. It means you are limited to relatively small angles of incidence. And this you have to take into account. You cannot say, yes, wonderful, we take only coated prisms, or the uncoated prisms are much better. We have to look for any specific application, what it is. And let's stress one more in detail the singles trace. We needed something like a benchmark. We used the famous Lager satellite orbiting at 6,000 km altitude, 428 reflectors in total, covering all the surface. The satellite is doing nothing than flying there at 6,000 km. It does not transmit radio signals, it does not receive radio signals. As I already told, it does not shot pictures. The standard target for all the satellite laser ranging stations within the International Laser Ranging Service And the effective cross-section of this satellite is defined to be 50 million of square meters. What does it mean, the effective cross-section? This is a definition. This is the area required for an isotopic scatterer at a given distance to deliver a signal equal of that of the considered laser reflector. Or to say it more simple, satellite 6,000 kilometers away, Lager's properties. In case you get the same signal from a white sheet of paper in the same distance of 6,000 kilometers, this sheet of paper would have to have a surface of 15 millions of square meters. Lager's has a distance of 60 centimeters. That means the enigmatic properties are within the retroflectors. The high directivity, as we call it, gives rise to this high effective cross-section. Otherwise, you would never get a signal back from that. Unfortunately, it is quite simple to express the effective cross-section for the center of the far field. Attention, it's the center of the far field we cannot use for laser ranging. This is proportional to the square of the diameter. It is inversely proportional to the wavelength used. This is squared again and scaled by pi quarter. So for a 9 millimeter prism, you get an effective cross-section of 0.18 million square meter at the same distance. This is from a recent study by L.Grundwaldt, who is the leading scientist in the world dealing with the theory of photoreflectors. Unfortunately, there are not very many scientists doing that, so I hope he will still be alive for a long time. And the effective cross-sections, as I told you, this angle of incidence, the acceptance angle, this is now the inclination of 0 with respect to the point face. In case we incline it, we have this the scale in 1,000 square meters, 400,000 square meters, effective reflective square. Then we have already a dip to 360. It's 20 degrees, we got to 180, 30 degrees of incidence angle get down to 70, and so on and so on. And you see also the shape of the diffraction far field pattern gets asymmetric with respect to the inclination angle we have. Those curves are making the intersection there, and in this direction. This is the red one, and this is the blue curve. These are the theoretical results for a half-inch coated prism with dihedral angle offset equal on all three back surfaces of one inch. Arc second, vertical scale, as I told you, 1,000 square meter. And you see from 400,000, we have come down to about 6,000, means already 100 times in case we incline the prism to a large degree, and we use signal again. All this because you cannot always assume that your light is going perpendicular into your reflector, gives rise to the losses. Few words, if we can verify what I've told you here. Unfortunately, it's a little bit tricky to align, but fortunately it is a relatively simple optical setup. We take a continuous laser. It does not necessarily have to be a Levy Billion arc, but it is quite green light. You need a polarizer in case you want to deal with uncoated prisms, and you need a short focus lens which focuses this light from the laser into a very narrow pinhole, 10 microns. The second very good astronomical objective is a long focus. This is here a Zeiss objective for amateur telescopes with a clear aperture of 80 millimeters and a focal distance of 1.2 meters. Has to share the same focus. That means those two lenses have to be exactly in the same focus. This is tricky, I can tell you. It's not so big a deal with a short focus lens, but with a 1.2 meter to find exactly the same focus, it takes some experience in some patients. This lens, this big astronomical lens, perform what we call the far field transformation. Because we cannot observe over hundreds or thousands of kilometers, because our laboratory is limited in size. And so we have to restrict ourselves to relatively short passes. And in case a very good lens which is large, let's say 1000 or at least several hundred times larger in focal distance than the short focus on objective, the far field transformation is effectively performed. And behind this you have parallel light, you have the CCR, the cube corner reflector or the reflecting prism, and the beam splitter will bring back a part of this far field which is transformed by this lens via a microscope objective into a CCD camera. Principle not so difficult. The light is going through the beam splitter onto the device under test, as we call it. Part of the diffracted pattern is transformed by this lens and is brought into the CCD. And attention again, the focal distances have to be matched precisely. So you can easily spend 2 or 3 days only aligning the setup. It's looking rather simple. You have an optical bench in a cellar laboratory. This is the CW neodymium light laser, the polarizer, the lens. And what you will see immediately behind is the 10 micron pinhole. There is the 1.2 meter size lens, the microscope objective. Here again is short focal distance lens with the pinhole immediately behind, the high quality astronomical objective, and the beam splitter, the microscope objective, and you can use even a consumer camera, a CCD. You only have to calibrate it somehow to know how many pixels are equivalent to how many arc seconds. And only to show you some results, how nicely this looks, we have taken the same time of a tenth of a second at a very low sensitivity. We have here some example for a 2-spot prism. I've told you in case you spoil only one of the dihedral angles, you get a 2-spot prism, diffractive far field. We have an uncoated prism. You see this is not a diffraction ring at all. We have an irregular pattern of spots, horizontal polarization, vertical polarization, the same prism, the same exposure time. That means also the intensity is dependent on the polarization in case of an uncoated prism. And here, really not visible now with the illumination going down, is the central lobe with practically invisible diffraction rings for a 10 millimeter prism. Taken with this simple optical stat. And before we make a short break, let's start with the problem of the incidence angle. I've shown you that the incidence angle plays an important role in the transmitted energy. How is the angle of light incidence with orbital altitude and elevation over the station? We assume that we have the Earth here with the center. RE is the radius of the Earth. The station is here and has the local horizon. The elevation angle is this one. 90 degrees minus the elevation angle is what we call the Zenith distance. The satellite orbits at an altitude of h, orbital altitude. RE is the radius of the Earth, and R, this is the sum of the Earth radius and the altitude of the satellite, is the geocentric satellite distance. And beta is what we are looking for, that's the angle of incidence onto the prism. Unfortunately, this can be expressed quite simply. You will see at the first view, because there is a sign with a 90 degree plus something, in case you have an elevation of 90 degrees over your station, the sine term gets 0, arc sine is 0. We have a perfectly vertical incidence, but unfortunately this is only the case for directly overhead flying satellites. And the effective area of a prism, S, is equal, more or less, to the entrance aperture square, let's say the entrance aperture, multiplied by the square of 1 minus the angle of incidence divided by the angle of cutoff. I told you that the cutoff angle is in the order of 50 degrees for a coated prism, so you will see that this is a non-linear relation between them. And what happens? We have an elevation in steps. 90 degrees I do not stress because I told you for 90 degrees the angle of incidence is 0 with respect to the prism moment. In steps of 10 degrees we go down towards the horizon, and let's have a look at an orbital altitude of 500 kilometers for a typical remote sensing satellite. Most of our satellites we are dealing with altitude. And of a GLONASS satellite at 19,100 kilometers. And you see, with increasing zenithal distance or decreasing elevation, the angle of incidence to your prism rapidly increases for the low Earth orbiting satellite and decreases fairly slow, practically not visible or not very much to be taken into account for a GLONASS satellite. That means for low Earth orbit satellites, you cannot use uncoated prisms. Why? I told you the acceptance angle is in the order of only 17 degrees. So for elevations below 70 degrees, you would already lose contact to an uncoated prism. For high Earth orbit, you can use uncoated prisms without any problem. You see, even for very low elevations, you never exceed the 70 degrees, the magic angle of incidence, where the cutoff will happen. And even for low Earth orbit laser reflectors, you will have to need to incline the prisms because 53 is already exceeding the acceptance angle. Means you have to give rise to some additional inclination of the prisms on board the satellite to avoid this cutoff. And how all this is performed, I propose we will have a look after a 5 to 10 minutes coffee break.